Okay, I just typed stat, so maybe you can see.
Okay, can we start?
I already typed stat.
Ah, cool.
Yeah.
All right, so yeah, it's the practical part of the linear regression chapter. Um, so normally we start the notebooks are began by importing packages. Here we import the essential data libraries like NumPy and Pandas, Matplotlib. These are the essential things to work with data. And after that, here's the new library that is introduced in this chapter. It's the stats models. Um, it's one of the most popular packages to build statistical models, as the name suggests. Um, so here are some usual imports. Nothing very very interesting actually. So and here we also import some functions from the book library islp. Then the lab introduces a function called dir, which gives you the everything in the everything defined in the memory. It's like the or in the namespace, like the variables, function names. So you cannot use these uh, um, these names in your code, basically. Um, and after that, here is uh, here we build. We can also use this function to know more details about the objects in Python. For example, here we define some array using NumPy, and we want to know the methods that this object holds. I think it's similar to the string function in R. I found it very similar to this, but here in Python
Yeah,
you
yeah,
just
yeah.
yeah yeah.
Mm.
Um, so yeah, nothing fancy, I think. Here's for example here you can try to execute some method which is sum to just sum everything in all the contents of array. And if you instead of executing the function, you can just add the a question mark to to get the help or the manual of this function. So you can know about the arguments that you can pass to this function. Very helpful actually. And now here's the we start to play with the data. We start by importing the Boston house prices dataset using the this function included in provided by the book package. And this dataset includes 13 13 columns, and we want to build a statistical model, a linear regression model, to predict the median house value using any of these columns. But we first start in a simple manner by just using one predictor to predict this median house value as denoted by mid v throughout this notebook. So we run this cell, and also using this method you can inspect the column names in your data, and also you can you can just see take a glance of this data set. And actually there's a cool plugin or extension to VS Code that allows you to display the data in an interactive way. And actually you can also change or edit make some changes on your data. And here you get some descriptive statistics of every variable. So very helpful. It's called Data Wrangler. Okay,
Yeah,
so
this is cool. Thanks.
yeah, actually it's made by Microsoft, so it's the compatibility with the VS Code is very good. And the same thing you can with objects in Python. You can use the question mark to get information about this object. Basically, these information are called in Python docstring. And here we define our first. We started to build our first model, this simple linear regression, and the convention is to build like to build like a data frame with two columns, one for the predictor, and the other one is called intercept to represent intercept basically, and you fill this with one values. So this data frame, or in mathematics it's called the model matrix or design matrix, is used to fit your linear regression model according to the ordinary least squares method. And yeah, here's how you define this. And you can see you just grab the predictor from your dataset and add another column for the intercept. So this so X here represents the design matrix, which you will use to just to fit the model using a built-in method provided by the stats models package. So here you just assign the variable that you want to predict, which is the median house prices, and the design matrix X, which is X, and you simply just run the fit method to get the results, to get the final results, and let me just results is just an object which holds a lot of methods actually. but the convention is to run summarize over this to get your coefficient, which is and this table, the resulted table, is pretty similar to what you have in the book, which gives you everything you need to interpret your model, like the t statistic and b value, and of course the coefficient. So here the coefficient value for intercept is just the beta 0, and the coefficient value for another for LStat here is the beta 1, the coefficient of the predictor. So any question on this? Anything to add? Okay, cool. So now the lab introduces another way to build the design matrix. And by the way, I just I brought this from Wikipedia. This is the mathematical notation to calculate the to estimate the coefficients using some matrix operations, which which are made automatically using this fit method after building the matrix and assigning it to the OLS function, which builds the model. And there is another way to build that design matrix, which is introduced here because the new method allows you to apply transformations on your predictors, which is very useful for handling non-linearity and like removing all outliers later. So simply we have imported previously at the beginning a method, a function called model spec, and here we just use this abbreviation MS, which allows us to build the metrics. Here we just we just assign the predictors that we want to use to build or to predict the response. And the same thing, we after that we just run we execute fit method to sorry, the fit here doesn't mean that you fit the whole model, but here you just apply the you run this before transform to apply the transformations, but at first we don't apply any of these transformations. We just sorry, we just reproduce the previous results in this new approach. So nothing new here, unless the syntax. Yeah, I added everything here. In the old method, you build X by using pandas. Excuse me. And in the new method, you use the model spec function to do that. And by the way, instead of running fit and then running transform, there is one method that you run that does the everything in one line. So the same thing here in the previous method, we fit the model like this, but now the whole code is written like this. So this is just an introduction, so you can so you'll be familiar with it in the next sections. So now we have the model, and we estimated the coefficients, and now we can predict, you know, the response using new some custom values. And to do this, we first define a vector or one column, a data frame with one column with the values that we want to use to predict the response. And after that, you sorry, and before pass it to the model, you also you have to convert it to the design matrix format using design.transform again. And now you can get the predictions using your model. Sorry, just I have to run this. And actually the results are the predicted mean. And you can after that, if you want to like know more about the uncertainties about around your results, you can estimate the confidence intervals with alpha 5 value of 5%. And here is I just wrote a script to actually the AI wrote this for me. Here's how you can visualize the uncertainties about around your predicted mean. So you can see if you want to compare this with another kind of uncertainty measure, which is the prediction interval. Sorry. You can find that the uncertainties here are much wider. Sorry, I have some issues with my throat.
No worries, no worries.
Okay, so here the prediction intervals is much wider because because it tells you where because the uncertainties here included here are the estimation error in coefficients along with the random variability in individual observations, or the epsilons in the model. So you just the only difference between two commands is that we pass a true value to this argument, the observations. Okay. So anything to add, or any question until this section?
No, I think it's clear, and I think visualizing the confidence interval looks interesting.
Yeah. I really like the intervals. thanks to ChatGPT.
Okay.
Okay, so there is some introduction also to define functions in Python. So nothing interesting here, but this is the notation to define like optional arguments, or if you don't have a fixed number of arguments, you can write this, and we want to we can then assign what we pass here to this plot function. The goal here is just to plot the linear regression model, which is basically a line. And there you can see the additional or the optional arguments are the last two ones. So now we want to like to examine the model. Like we want to see if there is any outlier, if we want to see if there is any outlier or extreme values in the predictions. Here's the plot to do that. You basically calculate the residuals, which is the difference between, you know, predicted responses and the real values. And you can see you compare, you can see here, you can visualize the difference or the distance between these residuals from this baseline, or from this, yeah, base like baseline around 0. And yeah, if you remember in the last sections in the chapter 3, the book mentioned something called the leverage value, which is an indicator for extreme values. So here's how you can calculate this and visualize it. So here you can see that, for example, this value is has a very high leverage value, which is an indicator that we should handle that either by removing it or something like this. Other other than that, because in data points with high leverage values affect the coefficient estimates when you fit the model. So that's why this section is titled with diagnostic plots, because you want to fix your model, or you want to make sure that your model is okay. And yeah, you can, for example, this value with the highest leverage, this data point with the highest leverage value can be obtained by this function. Actually, this is not the value, but the index of this data point, because the x-axis here represents the index of every data point in the data set. So now moving to the multivariate setting of the linear regression. Here we add another another predictor, which is age. Previously, we just added this one. So nothing special here. We just repeated the same steps. And yeah, I love this visualization. It shows you the hyperplane instead of the line, because now you have two variables, L state and the age, and here is the predicted Y value. I think we can just yeah, and we can. By the way, we can notice that there is some nonlinearity here. We can see there's something like a curve shape. Um, so now here we want to add all variables in the data set. So here we first define an object called terms. You just remove the response variable to include all predictors or possible predictors. And here you fit the model with all predictors and get the coefficient all coefficients. And now you can see that you have some predictors with high p-value, which indicates that uh, maybe it's not a good idea to include everything. We should like reduce the number of predictors or do something else. So here in the next so yeah when we added every possible predictor in this model, we found that, for example, age predictor has a high p-value. So let's by trying to dropping it from the model, we still have a high p-value for this variable. In the next section, we will do another transformations also. And now we jump to the goodness of fit metrics, like the R squared. If you remember, R squared ranges between 0 and 1. And it gives you the amount of variability that your model can describe. So if you have a higher value, in the most time, it's a good indicator. But of course, this depends on your application. And here's how you can calculate the residual sum of squares and residual standard error, which are another matrix as introduced in the chapter. And now, since we have many predictors in our model, we want to test if there is a multicollinearity between predictors, because when we build a linear regression model, it's not good to include correlated predictors. So variance inflation factor is a metric to calculate to find if there is a multicollinearity. And here's how we do this, basically. By the way, here the lab introduces some special notation in Python called list comprehension. It's like a shortcut to write a for loop in a single line, which is preferred by Python programmers. But of course, you can use for loop instead. And now we introduce how the way we put the interaction terms in the model. Um, so previously we were just adding terms without any multiplication operation. But here, for example, we want to model. We want to add this variable times this variable um, to see if this interaction term can can describe something in the data that we didn't um, we didn't pay attention to. Um, so of course now there is a dedicated coefficient for this term, as you can see here, and after that here we apply a polynomial transformation to one of the variables. This is the syntax to do so. You instead of just listing the variables that you want to include, you now applying, for example, here a poly function, and here we set the degree of the polynomial. So very basic. And here now you can see that after adding nonlinearity to the model, now the p-values here are very small, which is an indicator that now the model describes the data in a much better way. And here, by the way, the coefficients is very high, which is interesting, maybe.
So sorry,
Yeah, go ahead.
maybe if you could scroll up a bit. A bit.
Yeah, sure.
Yeah, so that coefficient, is it the linear case, and then the one is for the quadratic?
You mean we have two items here, with index 0 and index 1?
Yeah. So I'm thinking index 0 is when it's linear.
Yeah, so actually I didn't realize this. Maybe
Yeah. I
maybe
I think
you
I saw
mean
it. Yeah. So this like polynomial, right?
uh-huh.
So
So
what? Yeah. Go on, please.
yeah, so you mean that the in the first line here, lstat is existing in the model without applying nonlinearity, and here
Yeah.
is like lstat like
As a
primed to,
quadratic.
yeah,
Yeah. Yeah.
okay, rise to this to 2. Okay.
Yeah.
Okay, I got this. Actually, thanks to to know that because I didn't realize this. I thought that we just add the nonlinear form of the variable.
Yeah, we add it, but so it's easier to compare like this.
Uh-huh.
Yeah, like this is easier.
Okay, so in this way we like try all the possibilities.
Yes, yeah,
Oh, okay. Okay, cool. That sounds interesting. Thanks.
yeah, yeah.
Um, so in the
So
next section, go ahead, please.
yeah, and I mean you can even see the residuals, and also you can see the variance with the
Mhm.
first linear and the quadratic case. You could see.
You mean the actually
Yeah,
this part this I didn't get this part very well. So if you can add anything, it will be very very appreciated.
yeah. So you can see the analysis of the variance. So the first case is the linear case, and it doesn't
Uh-huh.
tell us much. And you could even see the p-value. We don't even have any p-value.
Yeah.
So you could see the quadratic case, the polynomial of degree 2 case. You could see the
Oh,
coefficients
okay.
are, yeah. You could see the residuals difference, and you could see the p-value. It's zero. So you could
Yeah,
see
it's
that.
very small.
Yeah, and even the
So
look at the F statistics is super high.
uh-huh.
Yeah,
Cool.
so it's better to use like a non-linear model for
Mm-hmm, mm-hmm.
this particular case, like to use a polynomial is
Oh,
better.
okay. So the here the 0 and 1 corresponds to the same
Yeah, so
indexes.
yes, yes,
Okay.
yes,
Uh-huh.
yes,
Okay, now
yeah,
it's very clear.
yeah.
Do you know what does the ANOVA stands for? So is it I remember that it was the like test for the difference between the difference in variance between two distributions, right?
Yeah, sure. It's analysis of variance.
Uh-huh. So
Yeah,
yeah,
that's it.
okay.
So
Okay,
we are
nice.
analyzing the variability into two models
Okay,
using it.
nice.
Yeah.
Mhm. So okay, so it's like the F statistic here is the equivalent to T statistic, but F is used
Yeah,
for ANOVA test.
for another test. Yeah, sure. Yeah,
Okay, super cool. Thanks a lot.
yeah, you're welcome.
Um, um, very interesting. So yeah, here's the same diagnostic plot again, but using the final model with the polynomial terms. Um, and yeah, finally here we learns how we learn how to add qualitative predictors. In the chapter there was like two or three ways. I don't remember, but the popular one is to add a dummy variable. But in programming, you just there is something called one-hot encoding to do this, and yeah, I remember it was very very straightforward. Here we load a different data set. It's about car seats. Um, yeah, baby seats, I think. Okay. And yeah, here we build a model with all possible predictors, and also we add two interaction terms, one for one between income and advertising, and the other one between price and age. And we fit the model, do everything, get the result. But the special thing here is that like stats models package handle the qualitative variable automatically. So we didn't like do any special thing here, but we can see here there is a variable called shelf location, which has which can take any of these three values, bad, medium, or good, and it automatically creates the dummy variable, let's say. So in the baseline situation, in the default situation, the value is bad, I think, but here there is two another levels, one for the good value and for the medium. So yeah, it's done automatically basically. So yeah, that's it. Thanks for listening, and sorry for taking your time.
No, it was really good. Thanks a lot. I learned a lot.
Okay.
Just
Sorry,
and
I have some cold and flu,
no, don't worry, it's fine.